Here's some help with Sapling Learning Chapter 7, question number 11. So this question is a bit like some other questions that we worked in class. So we've got a 0.5113 gram solid sample that contains a mixture of lanthanum chloride and cerium nitrate. And the sample was dissolved in water, and the solution was treated with potassium iodate, producing the precipitates lanthanum iodate and cerium iodate, which are both solids. For the complete titration of both lanthanum and cerium, 43.63 milliliters of 0.1223 molar potassium iodate was required. So calculate the mass fraction of lanthanum and cerium in the samples. We need to calculate the grams of lanthanum divided by the grams of the sample, and the grams of cerium divided by grams of sample. So the hints are pretty helpful here. It says let X be the mass of lanthanum chloride in the sample, and let Y be the mass of cerium nitrate in the sample. So what is an expression for the mass of the sample in terms of X and Y? So let's go ahead and write that down as our first step. Sorry, I'm having some pen issues here. So we got 0.5113 grams, and that's supposed to be equal to the masses of the two substances added together, right? So X plus Y, using the definitions of X and Y that are up here. So it says use the reaction stoichiometry, the two precipitation reactions, to determine the relationship between the moles of iodate added to the solution and the two metal ions. So we're going to need to know that, so I'll write that up here. So we've got a reaction between lanthanum and iodate. So let's first think about lanthanum chloride. Right? So if we take lanthanum chloride and dissolve it in water, then it's going to dissociate into its ions. So let's think about the possible ions that might be present. So we know that chloride has a -1 charge, right? So if it has a -1 charge, so why is it doing that? Alright, I'm having some serious pen issues here. So, oh, very odd. I'm sorry about that. Anyway, so chloride's going to have a -1 charge, and apparently I can't get my pen to go over that far. So a -1 charge, and so that means that if we reverse our charges, that lanthanum is probably going to have a charge of +3, and so we're going to get 3 moles of chloride. Alright, so that knowing that lanthanum has a charge of +3, we can guess what the precipitation reaction is. So lanthanum 3+ is going to react with iodate, IO3-, to yield, and I'll have to write that down here, our precipitate, lanthanum iodate, IO3-3. There's supposed to be a 3 there. Okay, so to balance this reaction, I need to put a 3 here in front of the iodate. So it's going to take 3 moles of iodate to react with every 1 mole of lanthanum. And the same thing happens with cerium iodate, and you can sort of see that here from the formula, that it's going to require 3 moles of iodate for every 1 mole of cerium. So now what we can do is write this relationship that they ask us to do between the moles of iodate and the two metal ions. So the total moles of iodate added has to be equal to 3 times the moles of lanthanum that we have present, plus 3 times the moles of cerium that we have present. Okay, and then the last part, it says the number of moles of lanthanum and the total number of moles of cerium can be expressed in terms of the mass of lanthanum chloride, X, and the mass of cerium, respectively. So we're going to convert basically moles into grams. We're going to use that relationship. All right, so here in this equation we've got moles of each of these species, and we want to substitute what those are. So we could calculate, just scroll down. So we can calculate moles of lanthanum by knowing the number of grams of lanthanum, and we're calling that X, and dividing it by the molar mass of lanthanum chloride. I like to write things in symbols since we're going to be having equations later. It's just easier to manipulate. So I'm going to call the molar mass of lanthanum chloride. Oftentimes we talk about the formula mass, so I'm going to use F for formula mass. And since X is our symbol for lanthanum chloride, I'm going to put a little subscript X right here. So F right here is the formula mass of lanthanum chloride, and we were told what that was in the problem. So for lanthanum chloride, the molar mass is this number. So that F of X that I'm talking about is this number, 245.26. We can do the same thing for the cerium, and let me write that down. 2 moles cerium 3 plus equals Y divided by, and we'll call it Fy. And so Fy again is the molar mass of cerium nitrate. And that was given to us in the problem. So what we're going to do now is substitute these two things, up into this equation up here. So we get a new equation that says total moles iodate is equal to moles of 3 times the moles of lanthanum, so that's 3 times X over Fx, plus 3 times the moles of cerium, and that's Y divided by F sub Y. Okay, so now we've got an equation. So we don't know X, we don't know Y, those are our unknowns. 3 we know, F of X and F of Y we know. So over here on the left-hand side of the equation, total moles of iodate, that's something that we can calculate, right? So that's related to how much iodate we added to the solution. And what we know from the question is a volume and a molarity, right? And so we're going to use that tool that we can go between from volume to moles, back and forth to moles, using molarity as a conversion factor. So that's what we're going to do here in this section of the problem now, to figure out the total moles of iodate that we added. And so in this problem, it looks like we added 43.63 milliliters. So 43, and we're going to convert that into liters. So 0.4363 liters, and we want to convert that into moles. So there's 0.1223 moles of potassium iodate, KiO3, per liter of solution, and that's the molarity, right? So we're using molarity, multiplying by molarity. And then we're just going to use the simple stoichiometry that there's 1 mole of iodate ions added, and that comes from every 1 mole of potassium iodate that we have, and that's just from the formula stoichiometry. And so I calculate that this equals 0.005336 moles of iodate. Okay, so again, I'm going to use some symbols here. So this is just a constant value, and I'm just going to call it A. So A is just a letter that stands for this thing that we know, the total moles of iodate. So total moles of iodate, that's what I'm going to be calling A. So I'm going to rewrite our equation. So we've got one equation that is the mass, the total mass of our sample, and that equals X plus Y. And then the next equation that we have is this one from up above that says that the total moles of iodate, which we've now calculated, it's this value A, is equal to 3x over fx plus 3y over fy. Right? So now what I have are two equations in two unknowns, and so this is like that problem that we've worked before, and so we need to go about solving this. And so the way to solve it is we're going to solve one of these equations. We'll pick this first one right here. We're going to solve it for one of the variables in terms of the other. So I just randomly picked x. It really doesn't matter. So x is equal to m minus y. So now what I'm going to do is take this equation and I'm going to substitute this in for x in the bottom equation. So when I substitute, I get a is equal to 3 times, and instead of x, I'm going to write what x is equal to, m minus y. And that's going to be divided by fx. Now, I'm a symbols guy, so I like to keep everything in symbols instead of numbers. But if you want to plug everything into numbers, you can go ahead and do that. I like to keep it in symbols because sometimes, not always, you'll find a way of simplifying some of the numbers. Anyway, so plus 3y divided by f sub y. Okay, so now what we have is one equation in one unknown, and we want to solve that for y. So I notice that I've got a 3 in both of these two terms here. Remember, term is things that are added or subtracted. So I'm going to divide both sides by 3. So I have a over 3 is equal to m minus y over fx plus y over fy. Right, so there's just a little bit of algebra. So I'm trying to get y by itself on one side of the equation. So right now I've got these two terms, so I need to combine the two y bits. And the way to do that is I'm going to need to put this over a common denominator, right, so that I can add these two fractions. So one common denominator would be to just multiply the two denominators together. So what I'm going to do here over here on this term is I'm going to multiply the numerator and denominator by fx. And then over here on this side, for this first term, I need to multiply the numerator and the denominator by fy. So fy divided by fy is 1, right? And so that's going to give us our common denominator. So I'm trying to solve this again for y. So I have a over 3 still, and then I have f of y times m minus fy times y. And then over here I have plus fx times y, f sub x times y. Alright, so perhaps these x's and y's are kind of, as subscripts, are kind of confusing, but keep them as subscripts, right? So this is a subscript, this is a subscript, and it's just telling you it's the formula mass of substance y, formula mass of substance x. And then in the denominator I have fy times fx. Okay, now you see that we can multiply both sides by fx fy, and so that's going to give us, as we keep doing our algebra, a times f sub y times f sub x, and that's divided by 3, and that equals f sub y times m minus f sub y times y plus f sub x times y. So you see that these last two terms both have y in them, so I'm going to combine them together and factor out the y. And so that gets me fy times m, and then plus f sub x minus f sub y times y. So you'll notice I rearranged the order here a little bit. So if I multiply the y back through here, you'll see I have a minus f sub y times y, and that's just this second term right here. So I just reordered things so I'd have a little plus sign over here. Now we still need to solve for y, so we need to get y by itself on this side of the equation. So it looks like I need to subtract fy m from both sides of the equation. Fy times m. And so that's going to equal fx minus fy times y. Okay, we're getting really close now. Remember, all these funky symbols, these are numbers. So at this point, it doesn't look like any of my symbols are going to cancel out or do anything nifty to make the calculation easier. So I might as well go ahead at this point and plug in numbers. Okay, so let me go down a little bit and do that, and I'll just get started with the numbers and let you finish the algebra from this point. So A is that number of moles that I calculated, and we're going to divide all that by 3. So I'm going to have a 1/3 out front, so that's just this 1 divided by 3 that's right here. And then I have A is my next term, and so A is the number of moles of iodate. Now it turns out it's a little tedious to make sure that all your units cancel, so we're just going to hope that we haven't made an algebra mistake so far, and everything should work out just hunky-dory. So I'm not going to include units on my numbers, which I generally don't advise, but in this case it's just a little bit helpful because canceling the units is tricky. So 0.005336, that was the moles, the total moles of iodate that we calculated earlier. Fy is the formula mass of substance Y, and Fx is the formula mass of substance X. So Fy is 326.132 grams per mole, and Fx is 245.126 grams per mole. If I scroll back up, you can see that they gave us those two values, 245.26 and 326.13. 326.13, yeah. So I looked that up, and I have a few more decimal places, but it doesn't matter. Okay, cool. So then we have our minus sign right here. So minus Fy again is this 326.132 grams per mole, and M is the total mass of our sample, and so that's the 0.5113 grams of the sample, and that is equal to, so there's my equal sign, that's this equal sign, Fx, which is 245.26, minus Fy, which is 326.132, and all that gets multiplied by y. So now you plug all this into your calculator. Everything is a number except for y. And so then you can solve for y. And finally you will know y. And remember what y is? Y is the number of grams of lanthanum chloride that were in the sample. No, sorry. Not lanthanum chloride. Cerium nitrate. X is the lanthanum chloride. Alright, so how do we find the X? We can go back to our equation that says X is equal to M minus Y. We'll know what Y is. M is our sample, so 0.5113 grams minus whatever Y came out to be, and that's the number that we just solved for here. Okay, we have done a lot of work. You might think we are done, but we are not, sadly. So there's one more thing. We need to calculate the grams of lanthanum so that we can divide it by the grams of the sample. And we need to do the same thing for cerium. So all of our lanthanum is in the lanthanum chloride, and we now know how many grams of that we have. That's going to be X, right? So when we solve this, this is equal grams of the lanthanum chloride, right? And so what we need to do now is figure out the grams of lanthanum. So let me tell you how we're going to do that. So if we know the grams of lanthanum chloride, we can use the fact that there is, we can look up the molar mass of lanthanum, and we find out that there's 138.9055 grams of lanthanum in every mole of lanthanum, right? And we're going to divide that by the molar mass of the whole lanthanum chloride compound. So that's 245.26 grams of lanthanum chloride in every mole of lanthanum chloride. Alright, so the mole numbers here, 1 mole is the same as 1 mole, right? So they're going to cancel out. The grams of lanthanum chloride cancel out, and this will tell you just what the grams of lanthanum are. So that'll get you the grams of lanthanum that goes in the numerator of this calculation. The grams of the sample, again, is just the 0.5113 grams. And then you need to do a calculation that is like this to figure out the grams of cerium nitrate. Sorry, just the grams of cerium. So we just need the grams of cerium. But you're going to start off with grams of cerium nitrate. And then you're going to use the ratio of the molar mass, grams of cerium per mole. You're going to divide that by the grams of cerium nitrate per mole. So you're just going to compare the molar mass of plain old cerium to the molar mass of cerium nitrate. That'll be the fraction of that total mass that is just due to cerium. And that'll get you your grams of cerium. Problem there. All right, grams of cerium at the end. And so then you'll be all set to do the final part of the calculation, which is where you plug the grams of lanthanum and you divide it by the grams of the sample. So good luck with this one, and check your algebra, make sure you don't make any mistakes. I ran through this problem first, and I had done one of those things where I reversed 2 digits in my molar mass, and I was getting the wrong answers. And I know it's very frustrating. So particularly in a problem this long, you make one small mistake somewhere, and you have to go back through and hunt and find it. But such is the way of complicated problems like this. And, you know, complicated problems are the stuff of real-world problems. So people pay you big bucks to be able to figure this stuff out. So it's good that you practice cutting your teeth on problems that take many steps like this one. So good luck.